In this video, we are going to talk about how to use vectors to represent arbitrary vector spaces, to represent points in arbitrary vector spaces. So to do that, I want to first start by talking about the linear dependence of vectors. And so we have a theorem that says that an indexed set V1, V2, etc. through Vp. So these are vectors. They're in a general vector space. There's at least two of them. And the first one is not equal to the zero vector. So there's at least one that isn't the zero vector. We say this is linearly dependent if and only if some vector Vj with j greater than 1 is a linear combination of the preceding vectors. So V1 and V2, etc., up to Vj minus 1. So if there's some way to build the jth vector as a linear combination of the preceding vectors, then it is not linearly dependent. Then it is linearly dependent. If there is no way to do so for every j, then it is linearly independent. So let's look at an example. So if we're thinking about a vector space that is built from polynomials of degree at most 1, we can look at a vector, a set of vectors. We'll call them P1, P2, and P3. And we'll define these vectors where P1 is just, these are, remember, polynomials, so we have to give them a variable. So P1 of t is just equal to 1. So no matter what t you plug into P1, it just gives you back 1. P2 of t is just equal to t. And P3 of t is equal to 4 minus t. Now, this is a linearly dependent set of vectors because I can write P3 of t as 4 times P1 of t minus P2 of t. So there's a linear combination of P1 and P2 that gives me P3. So this means that is linearly dependent. So this is an important idea, the idea of linear dependence, because basically if I think about all the vectors that in the span of P1, P2, and P3, or in the span of this setting, the P3 didn't add any vectors to the span. And so that's kind of an important idea, is because P3 is a linear combination of P1 and P2, everything that you could get to using P3, you could already get to without P3. And this leads to a definition. And this is an important definition. So we're going to say let H be a subspace of a vector space V. A set of vectors and I'm going to write this with a kind of a curly B, in V is a basis for H if two things happen. First, B is a linearly independent set. And second, the subspace spanned by B is all of H. So if you've got a set of vectors that are linearly independent and their span is the whole vector space that you're interested in, then we call that a basis for that vector space. So let's look at an example, that one that is a particularly useful example for us. If I think about the vector space R, let's do it with R3. So R3 is the vector space whose vectors look like this. So it's the vector space where the vectors have three real numbers. And I'm going to write down three vectors in this vector space. The first one is going to be E1, E2, and E3. So this is going to be my set of vectors. By tradition, these vectors, we use a hat instead of the arrow on top, which is a little strange, but that is a traditional thing to do. So I'm going to do it because you will see it. And these vectors are defined this way. E1 is equal to 1, 0, 0. E2 is equal to 0, 1, 0. And E3 is equal to 0, 0, 1. E1, E2, and E3 are called the standard basis. For R3. And essentially what this is saying is if you think about a three-dimensional graph, we're going to put x1, x2, x3 as our three different directions in our three-dimensional graph. Then what this is saying is E1 is the vector that goes 1 unit along x1, E2 is the vector that goes 1 unit along x2, and E3 is the vector that goes 1 unit along x3. And so if I think about any point in 3 space, say 1, 2, 1. If I think about mapping, looking at that space, well, I can do that by taking the vector e1, and then 2 times the vector e2, and then 1 times the vector e3. And that's where that point is in space. Notice the way I drew it, it kind of looks like it's on x2, but it's not. It's in front of it. It's more towards you. So that is this idea. So with this, we can start talking about some more theorems. So the next theorem I want to look at is called the spanning set theorem. And the spanning set theorem says, let S be a set of vectors so it's of a set in vector space V and let H be the subspace of V that is defined by the span of S. So H is the subspace that is defined by taking and every vector that you can get by taking a linear combination of V1 through Vp is in H. 2 things happen. First, if one of the vectors in S, let's say Vk, is a linear combination of the remaining vectors in S, then the set formed from S by removing Vk still spans H. This should be a fairly obvious statement. So if I've got some vectors at Vk that I can write as, say, let's say 2v1 plus 3v2 or something along those lines, then anything that I could reach, any linear combination of all the vectors in S, I can replace whatever the multiplier of Vk is to get to that point by changing all the pieces that added up to get Vk. And I would get the same vector. So so that doesn't change the span. Removing anything that is a linear combination of other vectors doesn't change the span. And the second says that if H is not equal to the vector space that is just the 0 vector, some subset of S is a basis for H. So basically what this is saying is I can remove, if there are any vectors that are linear combinations of the other vectors, I can remove that one and I can keep doing this one at a time. And when I have got it down to where there are no, where the set is linearly independent, that will be a vector. A basis, because it will still span the same space. Okay, so that is the basic idea of a basis. And now in the next section, we will talk about using bases to, and taking advantage of them, allowing us to use them to do something useful. So this next section is called coordinate systems. And we start with a theorem. This theorem is called the unique representation theorem. And so what the unique representation theorem says is that if we have a basis, let B equal some set of vectors that is a basis for a vector space then for each vector x in V, so for every vector in V, there exists a unique set of scalars C1, C2 through Cn, such that x is equal to C1 B1 plus C2 B2 plus etc. plus Cn Bn. So what this is saying is if B is a basis, then every vector in V can be written as a linear combination of the vectors in the basis, but it can only be done in one way. So this allows us to build a definition. And so this definition says we're going to suppose that we have a basis for our vector space, and we're looking at some particular vector x that is a vector in the vector space V. We say that the coordinates of x relative to the basis B sometimes this is written more simply as the B coordinates of x are the scalars C1, C2 through Cn such that x is equal to C1 B1 plus C2 B2 plus etc. plus Cn Bn. And so we would write this as vector x relative to the basis b can be written as C1, C2 through Cn. So what this has done is it has allowed us to take any arbitrary vector space and write it as a vector in Rn. So having a basis allows us to represent any vector as a vector in Rn, so that everything that we've talked about with vectors and multiplying that vectors by taking matrices times that vector and all of those things now work for any vector space. So this is a big deal because it means that anything that we develop for Rn, for the specific cases that we're looking at, apply to all vector spaces. Not only that, but we have a theorem that takes this a step further. This says let B equal B1, B2, up through Bn, be a basis for a vector space V, then the coordinate mapping x to x with relative to the basis b is a 1-to-1 linear transformation from V onto Rn. It's important that this is a 1-to-1 mapping. So this allows us to, we can use the coordinate mapping relative to the basis B to build this vector in Rn, but it's because it is 1-to-1, it means that after we've done whatever modifications we want to do, whatever proofs we want to do, whatever calculations we want to do, we can reverse that mapping to get back to the vector space that we originally were talking about. So this allows you to represent any vector space, any arbitrary vector space in Rn, and then undo that after you've done whatever calculations you wanted to do. Okay, so that's kind of the big idea behind behind the basis and coordinate system, is it allows you to take very arbitrary theoretical vector spaces and turn them into vector spaces in Rn. And that's where we're going to stop this video.